I did?
Yes. What did he change?
I don't think so.
The L and U?
Well, yes, and we talked about that a little bit yesterday, now that we've got the chain rule, so we'll talk about that again. So I've got 21, 22, 26, and 31 that I want to discuss. Those are those ones kind of at the end that are a little different than the main focus, which is, for the gateway test next week, just the derivative rules in general. So which ones before that, before 21, would you like to see?
17.
17. Okay, so tell me, Jordan, read to me what number 17 is.
F of x is equal to the square root of the quantity 1 plus 3x squared.
And
Squared.
just that like that.
Yes.
Okay? All right. So we're supposed to do the derivative of this, and of course the new thing we learned yesterday, the chain rule, basically just said anytime you have something on the inside of a function, we do the derivative of the outside, we do leave the inside alone, and we multiply by the derivative of the inside. So it's really important to understand what's the inside, what's the outside part of a function. And so like Casey was saying, you got to change the ln rule on the thing. And we had a discussion, several people were in here this morning, and I think got a lot of good out of being in here, so I would encourage many of you, again, I can't emphasize enough how much practice it takes to be ready for that test on Tuesday if you want to pass it the first time. Okay? Usually the people that pass it the first time really are solid with the rules to the point they can't believe they didn't get all 10 right. But they got 9 or 8 because there was an algebra mistake or there's something else. If you go into it wondering about the rules or not sure what something means or how to do something, getting 8 out of 10 is virtually impossible. Okay? I mean, I don't want to be too negative about it, but I can't emphasize enough how much practice it takes to feel good about it, to have any chance of getting 8 out of 10 on the first try. Okay? That means coming in and asking if you don't feel good about some of what we're talking about. But one of the things that was discussed in here this morning was if I have ln of 3x squared plus 7 or whatever the case may be. And the discussion was that, well, I thought the derivative of natural log was 1 over x. Well, no, the derivative of ln x is 1 over x. ln of other stuff on the inside, the rule is 1 over whatever that inside stuff is, and then times the derivative of the inside. So our new rule for natural log is ln of, and u just represents some stuff, like in this case 3x squared plus 7 would be the u. So the rule for natural log is 1 over that stuff, and then times the derivative of that stuff, whatever's on the inside prime, right, the derivative. So that's really the rule for natural log. So when you look at that sheet that I gave you, that's what you'll see is the rule for natural log. As a matter of fact, what I usually will say is, what's the rule for natural log? Well, it's 1 over. I don't say 1 over what, I just say it's 1 over the inside, right? What's the derivative of sine? Cosine. Right? We used to say derivative of sine x is cosine x. Right. If it's just an x on the inside, that's what it is. But it's usually sine of some other stuff. So the derivative is cosine of that stuff. And then times the derivative of the inside. Okay, press.
So is a lot of this stuff that was on our homework going to be on that test?
Absolutely. All like 1 through 20, whatever up to number 20, that is exactly what the gateway test is going to look like. F of x equals, this. F of x equals this, and now we're going to find f prime, right? So here we go. First of all, I would write this as, right? Because anywhere on that rule sheet, do we have a rule for square roots? There's no rule for square roots when it comes to derivatives, right? We have a power rule. So we write it to the 1/2 power. So f prime is, bring the power down in front, we leave the inside alone, we drop the power by 1, and then we times by, and I would always put parentheses there, the derivative of the inside. The derivative of the inside is that. So derivative of that is 0 plus, so I don't even write the 0, 6x. So I got the big set of parentheses all for that little 6x, but whatever. Okay? You would get it wrong on the gateway test if you stopped there. Because what should you do? 1/2 times 6 is 3. I would bring the x around in front. I don't really care if you bring the x around front with it, but it would make sense to. That's what we should have for our derivative. Now remember, I don't usually ever care if you distribute. Now, it's not really distributing there. It's just taking a 1/2 times the 6x. Now, if this would have been 6x plus 7, you could have distributed the 1/2, but you wouldn't have had to. Does it make sense? Because why distribute? Well, to get rid of the fraction. See, that's what happened here. We got rid of the fraction, maybe. You know, or we simplified by putting them together. I think distributing, now if that was 6x plus 4, you multiply by 1/2, to me that made it simpler, right? Because now there's no fraction in there. So I think it's not a bad idea to do that. So is there a little bit of gray area on the simplifying? Maybe. So if you don't know if you should, go ahead and do it and just do it right, and you'd probably be okay. More?
Can you do number 10?
Yes. Well, maybe. I shouldn't. Is it f of x? These all f of x? Tell me what 10 is, one.
Tangent, and then parentheses, square root of x, but it's like the third square
So
root of
cube
x.
root
Yes.
of just x?
Yeah.
Okay? Tangent of cube root of x. So I would first rewrite that as tangent of x to the 1/3, like so. So the inside function is the x to the 1/3, right? So the derivative, so we look up on our rule sheet, the derivative of tangent of u is secant squared of u. Now again, there's that lazy notation that we use, which is fine, but remember it's the whole thing squared. Secant of u, which our u is the x to the 1/3, we leave the inside alone, right? So we got that. Again, remember what that really means. What that really means is all that squared. That's what it really means. Okay, secant squared. And then times the u prime, right? Which is a derivative of that, which would be,
1/3.
there you go. I would be perfectly fine if you stopped right there. I mean, think about what your options would be. I guess you could flip that around to the bottom because of that negative power. Okay? Problem with doing that is people often do it wrong. I mean, if you ended up with a problem that was 6 plus x to the negative 2/3, I'm just thinking here, and then you took that and flipped that and put it under that 6, that'd be wrong because of that plus sign in it, right? You can't do that. If it was 6 times x to the negative 2/3, then you can flip it to the bottom. So sometimes people see a negative exponent, they just start flipping it around all over the place. And you can't do that. So I wouldn't mess with it. Okay, and the 1/3, there's nothing out here that it can multiply with, and so you could rearrange it, bring it around front if you want, but rearranging is not a big deal. Yes.
So you're totally cool with us leaving like negative exponents and stuff?
Yes.
Okay.
Okay. Now, again, if you have an answer that's got an x squared, and it's got some other stuff, and then over here's an x to the 3rd, right? To me, that should get put together as an x to the 5th. Same thing if this is an x to the 1/2 and this is an x to the 1/3, to me, those should get put together and add the power, right? But we don't have that in this case, right? So there's nothing, this is all squared, so it's got to be its own thing. And yeah, so you're done. You're done. Yes.
So would it be kind of wrong if we left it as secant squared?
You mean the way I had it with that?
Yeah.
No, that shortcut notation's fine. I just want to always constantly remind you what that really means. Okay? Because it's going to come up in class, man.
So is it okay if we put the negative exponent to the bottom?
On this problem, it would. As long as you do it properly.
Yeah.
That's my concern, right? Yeah, as long as you do it and it's correct algebra, absolutely. Okay, anything else? Yes. Okay, and 11, somebody wanted 11, okay?
That's
So
the ln thing.
let's do 11, then we'll do 12. So 11 is f of x equals,
It's ln, and then I think it's 4x squared plus something.
Plus 3.
Yeah,
plus 3. Okay, so again, the rule is ln of something, it's 1 over that, and then times the derivative of the inside. So the derivative of this would be 1 over 4x squared plus 3 times 8x. Now I didn't put parentheses because that 3 disappeared. But if this would have been a 3x here, then we'd had 8x plus 3, and then that absolutely would have needed to be in parentheses, right?
That's it.
But since it's just an 8x, we got that. Now that would be good enough. Now you could, it's probably smart to do that, and write it like that, but this would be okay. Okay. Number 12, Lauren was what? Or who asked about 12? Macy?
It's 1 over the square root of x squared plus e to the negative 3.
Okay. So that's the 1/2 power. It's on the bottom, so it would be negative, right? So this problem should be changed to, not really changed, but rewritten as that, right? So we rewrite this as that, and now we're ready to do the derivative. So we bring the negative 1/2 down in front. We leave the inside alone. We drop the power by 1, which would be negative 3/2, and we times by the derivative of the inside. So I make myself some parentheses so I don't forget, and then I fill it in. So the derivative of the inside is the red. That's that, right? So the derivative of that would be 2x. And then what do we know just out of habit from before? We're going to kick out a negative 3, right? But it's really chain rule. Really what it is the rule for E now, the new rule for E is, is e to the x, the derivative is e to the x. Well, now what it is, it's e to the u, the derivative is e to the u, and then times whatever that stuff is, because the inside of the e function is that whatever's up in the power. That's the inside. So the derivative of the inside right here is negative 3. So that's why we kick out or tack on the negative 3, because it's a derivative of the inside. It's the u prime. But we've done so many of those already that we just kind of automatically do it like so. Okay? And there it is. Now, again, could you take out negative 1/2 and distribute it through? Sure. You'll still have a fraction in there because of what you do with the 3. So I don't really care if you do or not. Okay? Distributing through is usually not really a big deal. Okay? All right. And again, this negative power, like Matt was saying, this negative power, since this is all multiplication, all these different groups here, I could flip that down to the bottom if I wanted to, right? Kind of like it was here, but it's not necessary. Okay? Now, somebody that was in this morning was asking about this. They said, okay, but what if this would have been a times sign in here? What if this would have been a times sign? Well, it would have stayed the same in here, but when you did the derivative of the inside, if that's a times sign, what would you have here? You'd have a product rule. So I needed more room, right? I wanted a bigger set of parentheses here for the derivative of the inside. I didn't have my product rule there. So that's where you can get that combination stuff going on. Okay, and 14. What do you got?
Quantity x plus ln
Raised to the 14. So the derivative, the outer function, this is the inside, the outer is the power rule, so I'm bringing 14 down. Leave the inside alone. Drop it by 1. Times by the derivative of the inside. The derivative of the inside is the red part. So the derivative of that is 1 plus derivative of that, 1 over x. Stop. Right? I mean, I could distribute the 14 over here. I can't because of that power there, but it doesn't really do much. I wouldn't worry about it. Is that okay? Does that make sense? Or?
yeah, it's pretty much whatever.
Okay, and again, what I would do is I would type that in, hit equals, and type what your and then grab what your calculator had and see if it says true. Did it not say true? Okay, well, I'll look at it. Is it still on your calculator? Okay, save it on there. Okay, anything else? 13. F of x equals
Cosine of quantity x to the 1/2 plus
Okay? So, the derivative, outer function is cosine, right? So the derivative of cosine is negative sine. So the rule for cosine of some stuff is negative sine of that stuff times the derivative of the inside. So negative sine, we leave the inside alone, times, I guess I got to change colors. Now we want to do the derivative of the inside, which is the blue part. So the derivative of that would be 1/2 x to the negative 1/2. And you're going to have to kick out a negative 1 because of what's there. E to the negative x. Right? We'll kick out that negative, which turns out to a minus. And again, nothing really that I can do. I can distribute that negative, I guess, over into that parenthesis, but not really anything useful. Okay? All right. Okay. Should move along here a little bit. So remember, Friday, we're back to full block, and it's going to be a lot of work time, review time, both together and separately, just individually as you work on some stuff. And Monday, a lot of that as well. Okay? But you don't want to wait till then, right? I mean, you want to feel pretty good going into those days so it can be just polishing and feeling better about it. Okay, let's go to 21. That was that whole big thing with the table. I just want to comment on that here quickly. So what happened is you had that table there, and you had the H row and the H prime row you had to fill in, and the X's on the top were 1, 2, 3, and 4, right? So let me just fill in the first entry in the H column and the first entry in the H prime column to help you there. Okay, so the first entry in the H column would be H of 1. Well, here's H, so H of 1 just means stick a 1 in for the X, so that'd be F of G of 1. So what's G of 1? So you go down the 1 and you go to G, and what do you got? What do you got? G of 1 is 4. So that becomes F of 4. The output of the G becomes the input of the F. That's what happens with composite functions. And so what's F of 4? 3. So there you go. So that's the entry there. So H prime of 1, before you can find H prime of 1, you got to have H prime of X. So here's H prime of X. So that was the key element in 21. If you didn't write this out, then you're in trouble, right? You're not going to be able to get it. So H prime of X is that. That's just a chain rule. Derivative of the outside, leave the inside alone, times the derivative of the inside. So H prime of 1, we put a 1 in for the X. So we'd have F prime of G of 1 times G prime of 1. These are especially favorite problems of the AP testers, right? These kinds of things where your calculator doesn't really help you, those kind of things where you really have to think through the process. Okay, so what's G of 1? We just said that. That was 4. So then this becomes F prime of 4. And then this is G prime of 1. So what's F prime of 4? I think it's 4. And then G prime of 1 is 3. 4 times 3, 12. So the H prime of 1 entry would be 12. And then you just repeat that with 2 and with 3 and 4. Okay? So that's 21. 22, that's this whole thing where we were just talking about with sometimes the inside needs a product rule or a quotient rule. I don't even remember what the question was on 22. It wanted H prime of 1, right? It gave you this was H and it wanted H prime of 1, right? So you got to find H prime of X. So we do the derivative of the outside, which is F prime. We leave the inside alone, times the derivative of the inside, which is that. Well, that's a quotient rule, so it's a good time to review the quotient rule, which is U prime V minus UV prime all over V squared, right? So U prime, the top prime to G prime, leave the bottom alone, minus top left alone is G, times the derivative of the bottom is 2x, all over the bottom squared. So you just write that all out. And then we're trying to find H prime of 1. So I put a 1 in for G here, or 1 in for X, so that'd be G of 1. Put a 1 in here, 1 plus 1 is 2. Put a 1 in there is G prime of 1. Put a 1 in there is 2. Put 1 in there, g of 1, 2 times 1 is 2, and then the bottom 2 squared is 4. So now we got to look, and then I think they gave us a bunch of this, right? What was g of 1? G of 1 is 2, so 2 divided by 2 is 1, so this becomes f prime of 1. G prime of 1 is 4, and g of 1 was 2, we said. So 4 times 2 is 8, 2 times 2 is 4, 8 minus 4 is 4, 4 divided by 4 is 1. Worked out nice. And then what's f prime of 1? They said 7. F prime of 1 is 7. 7 times 1 is 7. So therefore, h prime of 1 is 7. Right? So that's what a problem like that looks like with those function values. Okay, 26. What was 26? Oh, we had that G graph there. No, F graph. We got the little F graph, and they told us G was this, and they wanted to know in 26 where is G prime equals 0. Well, here's G prime, right? Derivative of the outside, F prime, leave the inside alone, times the derivative of the inside. Where does that equal 0? Well, two things multiplied to equal 0. One of them's got to equal 0, right? So either f prime of x squared is 0 or 2x is 0. Well, that one's easy, right? So that's one value of x, where g prime would be 0. When is this 0? Now forget the x squared for a minute. Just ask yourself, when is f prime 0? Well, that's the f graph, right? So that means when the slope is 0, that's when?
2.
Now, we're really used to that question, but we're only used to it in this context, right? So we would always say, well, when x is 2. But in this question, it's not when x is 2, it's when what? It's when x squared is 2, right? In other words, on that f graph, it's clear to see that f prime of 2 is 0. Would you all agree with that statement? F prime of 2 is 0. Okay? But I think we should show Miss Rudder, I think she deserves to see the German shorthand here. So, be the highlight of her student teaching experience. So, right here, right? The German shorthand is the same in those two statements, right? Where f prime of the German shorthand is 0, it's 2. So x squared has got to equal 2, which means x is plus or minus root 2. So they ask for the x values where g prime would be 0, and that would be it. There'd be 3 of them, okay? So when we say, where is f prime 0, we say, well, when x is 2, what we really should say is when the input is 2. That's what we should say. Instead of x is 2, we should say when the input is 2. So in this case, our input is x squared. So it's when x squared is 2. Okay? And then we solve that, we get the plus or minus root. Okay? So that was 26, kind of an interesting take on that. And now 31 is a very similar kind of situation. 31, they give you an f and a g graph, and they say, where are the stationary points of h? So they tell you h is this. Well, it's the same question we just had in 26. The stationary points are when the derivative of h is 0. So I wrote out derivative of h. Where does it equal 0? Well, when one of these is 0. Well, the first one is easy, so let's do that, or the second one actually. Where is g prime of x 0? Well, here's the g graph. Be right there. Where's this one? Did it say it's in between there? Yeah, it's hard to kind of see. So is this one at what? Negative 1.5? So it looks like at negative 1.5 and at 2 is where g prime would be 0, right? The slope would be 0 on the g graph. So that one's easy. But the one that's a little trickier is this one. Where is f prime of g of x equal to 0. Well, forget the g a minute. That's kind of like the x squared on the problem a minute ago. Our input is g of x, right? So let's just ask ourselves, when is f prime 0? Here and there. So the f graph has a slope of 0 when this input is 0 or 2. Does that make sense? Instead of saying when x is 0 or when x is 2, we're saying, okay, when is f prime 0? When the inputs are 0 and 2. Well, the inputs we're looking at is g of x. So it's when the inputs are 0 or 2. So it's when g of x is 0 and when g of x is 2. So we got to keep going.
What about at 5?
It looks like maybe 5 also. I would agree with you. Now, if you didn't see that and you left that one off, I would be okay with that. But you're right. It looks like maybe it flattens there. So now we're asking ourselves, when is g 0? Which means the output of g, right? When is the output of g 0? 3 places. That's at -4, 1, and 5. When is g of x 2? Isn't it there and there? So that'd be when x is 0 and -3. And when is g 5? Never, so it didn't run that. Right? G never has an output of 5. So look at all those. 2, -1.5, 0, -3, -4, 1, and 5. At all those places would be stationary points of h. We have no idea what the h graph looks like. We don't have a picture of it. I mean, we could maybe plot a bunch of points and maybe try to come up with something, but there you go. Interesting. Like 7 of them. Stationary points, right? Okay. So that's a really, that probably makes you think there a little bit. Or a lot. Okay. On to the next thing. What the heck? We're just starting to get the hang of this, so, man, let's do something new. Right? Isn't that the theme?
Yeah.
Sort of. As soon as we start thinking we know what we're doing. All right, but that's, I mean, that, I think we're better off doing that and then just really use our time Friday, Monday to be able to work on stuff, okay? And review and put it all together. All right, so we're talking about implicit. This thing we're going to do today is implicit differentiation. If you look at the derivative rule sheet, we only have 3 more rules to add at the very end. They're inverse, arc sine, arc cosine, arc tangent, and they're pretty easy to remember. So that'll be the new thing tomorrow. That won't take very long to do. So we'll already be beginning to be able to review and stuff like this. This thing is kind of this outlier. It's a technique of doing the derivative we don't have to do very often, but when it comes up, we need it. There's going to be some things later on where we need to be able to do it. Implicit comes from implied, okay, which means it's kind of opposite of explicit, okay. What we've been doing would be, I guess, explicit differentiation. We've been doing, here's our function, here's y equals, and then we do the derivative, okay. Implicit would be when we have functions that are not explicitly defined. So here would be the difference. So on the left side, we have f of x equals x squared minus 2x. We got our output on one side, f of x. We got our inputs on the other side.
Are you recording?
I am, thank you. I know. And that was kind of here. So on the right, then you have an implicitly defined function, which I put function in quotes because it might not be a function. For example, an ellipse, a circle. Those are not functions. They fail the vertical line test, but they still have slopes, right? They still have slopes. A sideways parabola is not a function because it fails the vertical line test, but it still has slopes at various points. So it still makes sense we should be able to do a derivative. We should be able to find y prime, dy over dx, on those functions. Okay? So now, clearly on the one on the right there, I could solve that for y pretty easily. That's not even a sideways parabola, but I've got some other ones here. Okay? That middle one is a hyperbola, or the one on the right, excuse me, the bottom one on the right is a hyperbola. Okay? Kind of a tilted hyperbola. No, wait a minute. That might be an ellipse. Actually, that's an ellipse, I think. That's a tilted ellipse. And it would have slopes. And there's no way you could get y by itself. And so a lot of these, we've been using f of x, g of x, h of x a lot, but we could have been just using y as our output, right? So we'll see that a lot when we write functions or relations that are implicitly defined. A lot of times they have this. And we could not get the y by itself on this bottom one here. This one we could. We could get the y by itself and just do our normal derivatives. Explicitly do the derivative. But here we're not going to be able to get y by itself. No matter how much we try, we cannot get y by itself here. There's going to be a mixture of x's and y's. So there's got to be a way to still find y prime. Okay? Now we haven't really thought about it, and then you don't have to write this down, but x is always going to be our input variable, y is our output. So when you get a mixture problem like this, it's like which one is which, you know? If these were a's and b's, how would you know, kind of thing. So, you know, we always have to define which one is our dependent variable, which is our output, and which one's our independent variable. Independent means when you make a table of values in Algebra 1, you pick anything you want for x. That's why it's called the independent variable. It can be anything. Then the y is dependent on what you pick for the x. So that's why y is called the dependent variable. Okay, but back to the point. We've never thought of it this way, but when I look at this equation and I say do the derivative, right, we would just write down on the left side, we would just write down y prime automatically because we're doing the derivative of y, which is y prime. But now we're going to bring a little different meaning to that, a little different thought process to that. What I'm going to tell you here is we're doing the derivative of both sides. You're going to hear me say this term. We're going to do the derivative of both sides. Well, what's the derivative of y? Well, it's y prime, right? dy over dx. Now, it's going to be very important when I say do the derivative of both sides with respect to what? What's your input variable? And I've talked a lot about how that dy over dx with respect to x, but it hasn't really meant too much to us. It hasn't been that important. Now it will be. So by saying do the derivative with respect to x, we're telling you x is the input variable. So on this side, we would do our normal derivative, just like that. On the left side, what's the derivative of y? Well, with respect to x, the derivative of y is y prime. Okay? What's the derivative of x? If I this is interesting. What's the derivative of x? If I just tell you, what would you have said? Derivative of x?
1.
You'd say 1, right? Now, what was missing from my statement there was, what are you doing it with respect to? Right? You assumed with respect to x, right? So then it would be 1. And it makes sense because in Leibniz notation, that would be this. Leibniz notation, if you were going to say take the derivative of x with respect to x, it'd be dx over dx, which of course seems like that makes 1. But if I tell you to do the derivative of y with respect to x, that would be dy over dx, which of course is another way of writing just y prime, right? Remember when we were doing those Bismarck problems and we had the east-west thing? Well, we could think of that east-west down here as our x-axis. And we could have a function that was x of t. And we could have, t squared plus 7t or something like that, right? Now I might ask you to do the derivative of that equation, right? The derivative of x. What would you tell me to write in this case? We would write x prime, wouldn't we? You see the difference? In the one case, I say, what's the derivative of x? And you tell me 1. That's because x is the input variable. Derivative of x with respect to x. Here I would be doing x prime, which would be the derivative of x with respect to t. That's a different animal. The x is the output variable. See what I mean? So the output variable, when you do the derivative of it, gets a prime on it. The input variable, you just do your normal thing. So it's possible you could have an x prime if x was the output variable. Okay? So that's going to be a really key element of how we do this. All right, so let's do some examples here. So, my directions to you here are do the derivative. So, what would you write in this case? Y prime equals, no,
What?
1. Because what were we doing there? When I said do the derivative, I didn't say it, but what was meant there was that we were doing the derivative with respect to x, right? So we're getting dy over dx, and the derivative of x with respect to x would be like doing dx over dx, which of course is 1. Okay, on this one, oops, that of course, dx over dx would be 1. So what would you be doing here if I said do the derivative? You'd assume it's with respect to t. This would be the derivative with respect to t, and the answer would be still 1. But there we were doing dy over dt, right? We're doing the derivative of y with respect to t. So again, it's still y prime equals 1. What about this one?
Same thing.
Same thing. This would be y prime equals 1, but there we would be doing dy dz, right? Equals 1. So again, what is your input and what is your output variable are really key elements of this. It's been mostly easy because most of the, for us so far, because it's been f of x, h of x, g of x, and x has always been our input variable. Okay? All right. So now we get to this problem. Now, the easy thing to do on this would be to just divide by 3 over here and get the y by itself, right? But and the same thing here, I wouldn't divide by, but what could I do on this one? I could square root, and I'd have to remember to plus minus square root, and it would be messy, because it'd have a 1/2 power, I'd have to do a whole chain rule thing, it would be kind of messy, but I could do it. But we are going to run into some, like this one, where we don't have that option, where we can't get the y by itself. So let's study on some simple ones what we could do, okay, instead. So now the problem's going to be, how do I do the derivative of 3y? Anybody got a guess of what I would do? Remember, with respect to x. 3y prime, that's right. Now let's think about why that would be. Well, because whenever you have a number out in front, it just hangs out there, so the 3 just hangs out there. And what's the derivative of y? Y prime, because we're doing the derivative with respect to x. Right? We're doing the derivative with respect to x. Okay? So, actually I wanted to write that over here. So, the derivative of y would be 3y prime. Now, if we take the y out of there and put an f of x in its place, I think you would all agree then how easy that actually is. If I gave you 3f of x and I said do the derivative of that, wouldn't you write 3f prime? Wouldn't that make sense? I probably should have started with that. I think you all would have said 3f prime. Just like those f and g and h problems we were doing today. Okay, so let's look at this one. Y squared. Now, I'm not sure what you guys would do if I told you to do the derivative of y squared. So let me substitute and write it this way. Now, would you agree these two represent basically the same thing? Right? So now you guys do the derivative of this. 2 f of x to the first. Wouldn't you have to do that? Doesn't that look like what we were just doing in today's homework, the chain rule? You got some stuff on the inside. So doesn't that look like it should be 2, bring the 2 down in front, leave the inside alone, the f of x, and then times the derivative of the inside, which would be f prime. Now, what would be the equivalent of that up here? So let me erase that 1. It kind of looks like a prime. So what would the derivative of y squared be?
2y times y prime.
I could put y prime of x, but the whole point of using y is so we don't have that whole function notation. Isn't that the derivative of y squared then? Shouldn't it be? It certainly makes sense down there, so why wouldn't it make sense there? And we usually run into a little trouble with this. Okay? We have to think of the y as our output variable. So we have to think of it like some stuff. The y is some stuff, some x's. So it's like our u. So when we do the derivative of y squared, we're really bringing down the 2, leaving the y alone, and then doing the derivative of the y, which is y prime. So the derivative of y squared, when y is the output variable, is going to be 2y y prime. Now I usually say it to people this way. When you're doing the derivative of the output variable, do the normal derivative and tack on a y prime. Because that's really what it comes down to. So in other words, what would be the derivative of sine y? Again, assuming we're doing it with respect to x or t or something else. Y is the output variable. What's the derivative of sine y? What's the derivative of e to the y? E to the y. What's the derivative of ln y? You see what I'm saying? When you've got a y, an output variable in there, because that's what we're going to have, because we're going to have this mixture. We're going to have the input variable mixed in with the output variable. So when we do the derivative, we do the input ones, the x's, like we always do. There's no reason to tack on an x prime, because what is x prime? 1, right? X prime is just 1, if x is the input variable. Or t prime is just 1, if t is the input variable, because it would be dt over dt or dx over dx. It's just 1. But y prime is y prime. It's dy over dx. So we tack on a y prime if we're ever doing the derivative of the output variable. Okay, just do the normal derivative, tack on a y prime, and you'll be in great shape. Okay, so the normal derivative of 3y would be 3, tack on a y prime. So you get 3y prime. The normal derivative of y squared would be 2y, tack on a y prime. If you do those things, you're going to be in great shape. So here we go. Let's try it with one right here. So here I've got a basic sideways parabola, which is this equation right here. So the instructions for you are going to be do the derivative of both sides with respect to x. In this case, we'll just assume x is always the input variable if there's any choice. So do the derivative of both sides with respect to x. So what's the derivative of x? 1 minus 2y y prime. Now, I see people do this a lot, 2y and then put a big dot and y prime, like there has to be this separation there. No, it's just 2y y prime, right? Like that. Equals, what's the derivative of 0? 0, right? So we can't forget we're doing the derivative of both sides. Now, what are we really interested in, though? What are we trying to find? I mean, right? We get lost in the weeds here a little bit. We kind of forget what we were doing. What's our goal here? Y prime. We're trying to find the derivative, right? We're trying to find y prime. That's our goal. We're trying to find y prime. So we're off to a good start, but we now have to solve for y prime. So maybe I'll add that over to the other side. And then what? Divide by 2y. And we got that. So now, just curious here. Say I wanted to find the slope when x is 2. Well, there's actually 2 points when x is 2. This isn't a function. It fails a vertical line test. There's actually 2 different answers for the slope. So what would I do to find the slope when x is 2? Would I plug a 2 in here? I can't plug a 2 in here because that's the y. So how do I find the slope? I have to put a 2 in for x where? Back in the original, right? So I'm going to put a 2 up here for x. So I got 2 minus y squared equals 0. I got 2 equals y squared. I got y equals plus or minus root 2. So what I'm going to get here is I'm going to get 1 over plus or minus 2 root 2, right? And does it make sense I would have a plus and a minus? Because right here I'm going to have a positive slope, and right here I'm going to have a negative slope, and it doesn't look like they have the same steepness. It's just that one is positive and one is negative, right? So whatever that number is, that would be the slope at those 2 places, right? So that is implicit differentiation. Now, I purposely picked one that we could have gotten y by itself. We could have done explicit, which is our normal way of doing derivatives. I could have done what I did right here. I could have added that y squared over to the other side. I could have square rooted both sides, got plus or minus square root of x, right? Which is the same as plus or minus x to the 1/2. Now let's do the derivative of that. Bring the 1/2 down in front. X to the negative 1/2. I could have done the derivative that way. Okay? Is that the same thing as this? Absolutely. Because if I look at this, I could have taken my y prime here. I could take this negative power, flip it down to the bottom. I got plus or minus 1 over 2 square root of x. Now, what is square root of x? Plus minus square root of x is y. So if I take this plus minus and this square root of x and replace it with a y, I get 1 over 2y. They are the same thing, right? And if I want to know the slope at 2, I can now take it, when x is 2, I could put a 2 right in here. And I'd get 2 to the negative 1/2. Well, let's put it in here. Let's put a 2 right there. Look what I get. Plus or minus 1 over 2 root 2. Right? So I could have done the blue, just our normal way of doing things, by getting the y by itself first. Problem is, not all times will you be able to get the y by itself like in this problem. So we have to have this thing called implicit differentiation to handle those situations. Okay? And it's going to come in handy in some other areas we go to as well. Okay? So let's do a really interesting one. Let's go to this one. This is an ellipse. It's kind of some sideways, tilted kind of thing. This will be our last one, and then actually give you a little bit more time to start. And I like this one because it brings in one little kind of a twist here that we have to do. So no matter how we would try, we cannot get the y by itself. Okay, so this would be a really good one to have in your notes, because out of the 10 on the gateway test, no more than 2 of these. So a person could theoretically get 8 and bomb both of these. I don't think you should, because I don't think they're going to be that hard, because there's not going to be much variation. Chances are there'll be one that'll look very much like this, and if there's another one, it'll probably be a simpler one like this or the one we just did. Okay, this would be the hardest one you could see on the gateway test. Okay? Now, so what do? We do the derivative of both sides. So we start here. What's the derivative of that? 10x. Now, here's where this gets tricky. Does anybody have an idea on this one?
Minus 6y prime.
Minus 6.
What are you forgetting? You're doing it perfect.
6y, y prime.
No. No.
Oh, you have to do the multiple.
Product. It's 2 functions multiplied together. It's x times y. Y is its own function. X is a function. It's a product rule. Now, here's what I would suggest. I would attach this negative to that 6, and I would treat that as one thing and treat that as one thing. Because if you don't, that minus sign, you're going to have to remember to distribute. Because remember, the product rule has a plus in between. So I would treat this as negative 6x times a y and do your UV product rule. So here we go. Derivative of the first, what's the derivative of negative 6x?
6.
Negative 6, with the y left alone. Plus negative 6x, so that'll actually turn to a negative. So negative 6x left alone, and what's the derivative of y? Y prime. Now, it's not y prime. A lot of times people do that. Think of the normal derivative of y would be 1, just like the normal derivative of x is 1. So the normal derivative of y is 1, and then tack on a y prime. Or just think the derivative of y is y prime. But I always see that when people have 7y, they think that's 7y, y prime. No. The derivative of 7y is 7. Tack on a y prime. Okay? All right. If it was 7y squared, yeah. Then you'd have 14y as the normal derivative, and then you tack on a y prime. Okay, anyway. So there's our product rule right there. Not bad, not hard. Plus, what's the derivative of that? Careful. 10y is the normal derivative, and then tack on a y prime. So 10y, normal derivative, tack on a y prime. Equals, careful, 0. Derivative of 16 is 0. Don't forget about making that a z. Okay? Now we need to solve for y prime. Now, people sometimes struggle with this. I will just say this to you. If you're going to solve that, what do? You get the x's together on one side, and you get the other stuff over to the other side, right? You get the x's on one side, you get the other stuff to the other side. Well, that's what we do here. We're going to get the y primes on one side, and we're going to get the other stuff to the other side. So I'm going to leave the negative 6x y prime plus the 10y prime on this side, and I'm going to get the negative, put that over there, that'd be negative 10x plus 6y. Now, your answer may look a little different if you get them on the opposite sides of what I did. If you move the y primes over to the other side, to the right, and leave the non-y primes to the left, then your signs will all be different than mine, but it'll end up being the same in the end. Be like having negative 6 over negative 3 or 6 over positive 3. Either way, that's the same answer. Okay, so what do we do on the left side then? Take out a y prime. And you get negative 6x plus 10y. Over here you just have whatever you have. And then you divide by that big quantity. Every one of these problems will look the same when you get into this way. Your y primes, you'll have 1, 2, or 3, probably at the most, y prime terms. Leave them together. Move all the non-y prime terms to the other side. And then you take out a y prime, and then you can divide. And then I would suggest, I'd pick kind of a bad one, well, not a bad one, but I would say you could simplify that. Because what could you factor and cancel? You could take a 2 out of the top and the bottom and cancel it. So it really would be negative 5x plus 3y over negative 3x plus 5. So now on this ellipse, if I wanted to know the slope at a certain point, I would need to know both the x and the y value of that point, and then I could plug it into there, and I could actually find the slope. But on the gateway test, you won't have any of that. It's just do the derivative, so there it is. But that's what they're typically going to look like. There's not very many practice ones of this in the book, so I'm going to pretty much give them all to you here as the homework, and so you can work on those. And then there is a website that's got a few more, and I've got a couple things on a website where we can you can get a little more practice on those. Okay, so on your homework here, if you would turn in your book first to page 195. Okay, see this page here, and it goes over onto the back a little bit, but all the way from 1 through 59, 1 through 59 would all be examples of functions we should be able to do the derivative of for the gateway test. Okay, so what I'm going to assign you on the assignment sheet, the line that says 3.3, so the next line down on the assignment sheet, okay, which is the implicit differentiation ones, the new ones for today. And then pick out any, I don't know, 10 maybe. That might be a lot, but, you know, I don't think, I mean, if you really want to do well in this, you probably need to do at least that many. You know, just randomly pick, maybe pick ones, depending where you're at. If you want to challenge yourself, pick ones that look hard, you know, and we'll do that throughout the course of the next several days. Part of your assignment will always be, hey, go to page 195 and pick out a few more to do. Okay, and then, you know, on Friday, part of what we'll do is have people ask me about certain ones they tried that they thought were especially difficult, maybe on that page, whatever they thought might be good. So use your calculators or pick odd ones if you want to look in the back, whatever. Okay, so 3.3, the implicit differentiation, then page 195, pick any 10, and get to work on those. Okay, that's pretty much it. But as far as new stuff, when it comes to the gateway, we have 3 new rules here at the bottom that work just like all the rest of our rules do, so they're just a matter of memorizing them. Other than that, you know, you've been exposed to most everything you're gonna need for the gateway test. Now it's a matter of practice.